My name is John Kimball from the University of Montana, and today I'll be talking to you about developing a global data record of landscape freeze-thaw cycles from satellite microwave remote sensing. Just to give you a brief summary of the overall presentation today, I'll be talking about the ecological significance of a landscape freeze-thaw signal and the ability of satellite microwave remote sensing for freeze-thaw detection on a global basis. I'll also be talking about the motivation and objectives for developing a long-term global satellite freeze-thaw Earth system data record with sufficient accuracy for being able to assess environmental change. I'll be giving a method summary of the overall database assembly, the algorithms, and the product format development. And I'll be talking about, just as some examples, of some selected results and applications, particularly ecological applications of this freeze-thaw Earth system data record that was developed. That will include accuracy and quality assurance of the overall product on a daily basis and how we assess that. I'll talk about using that record to assess global freeze-thaw climatology and trends for the first time from satellite microwave remote sensing. And I'll also talk about an ecological application looking at vegetation productivity impacts of changing freeze-thaw cycles that we're seeing in the record. I'll also give an overall summary of the freeze-thaw data record and planned updates that we intend to be making to the record over the next few years. And then I'll leave off with some selected online resources available to the user for further exploration. So why satellite microwave remote sensing for freeze-thaw detection? Well, first, when we think about satellites and remote sensing, we often think about optical and infrared wavelengths. That's really what, in the visible spectrum, what the eye sees and what we're used to seeing, say, through a camera, and extending into the infrared wavelengths as well. One of the problems we have, though, for remote sensing and optical and infrared wavelengths is this problem with clouds. We live on a cloudy planet. So that's a real challenge for regular biospheric monitoring over a global domain from optical infrared satellite sensors such as MODIS, Landsat, and other types of satellites and sensors that we're used to. And the other issue with optical infrared remote sensing is not just with clouds, but really that type of remote sensing is dependent on solar illumination. And if you think about certain areas, particularly at high latitudes in the extratropics, significant portions of the year are fairly low solar illumination, low solar angles, and low illumination, particularly in these long winter months. And so this is just an example from VIIRS, but this is really problematic with any kind of optical infrared sensor. You see at high latitudes for this particular time of year, which is November, that we really have no signal at high latitudes, so that's been screened out. It's represented in gray here at the top of the globe. That's lost information because the solar illumination is insufficient to retrieve an adequate signal. Well, that's not the case with satellite microwave remote sensing. So there's a number of complementary features of satellite microwave remote sensing that is very synergistic with optical infrared remote sensing. First, when we're talking about microwaves, and what I've got here is just an example of the electromagnetic spectrum. Okay, and when we're talking about optical remote sensing, we're really dealing with a very small portion of the electromagnetic spectrum. Okay, right here in the blue, green, red, near infrared, or extending into the near infrared. When we're talking about microwave remote sensing, we're really dealing with much longer wavelengths of the EM spectrum, out to 1 to 30 centimeters approximately. And we're dealing with a very large atmospheric window at those frequencies. That atmospheric window, what that means is that the amount of atmosphere absorption of this land surface emission of microwave energy is pretty minimal. And so we get a very good signal without much atmospheric contamination of that signal of the land surface. And that's very good. Okay. One of the issues, though, is that most of the natural emission and reflectance of energy from the land surface is really at those shorter wavelengths. And that's why optical remote sensing has somewhat of an advantage in terms of the strength of the signal, is that most of the sun's reflected energy is in these higher frequencies or shorter wavelengths in the optical section of the EM spectrum. And what that means is you get a very good signal. But natural microwave emissions are a much longer and lower portion of total emitted energy of the land surface. And so because of that, for passive microwave sensors or radiometer sensors, we have to increase the footprint size, the field of view of the sensor, to coarser spatial scales to increase the amount of signal that we're getting from the land surface. And so that tends to degrade the resolution from which we can get remote sensing information from. Now, microwave remote sensing also involves both active and passive or radiometer sensors. What I'll be dealing with in terms of constructing this record and talking about mostly today, we'll be dealing with the radiometer side of things. Though radar, I'll also give some examples. And really the difference here is that from a radar instrument or an active sensor, the energy that's being emitted from the sensor is sensor dependent. And so that energy is being emitted to the surface, bounced off the surface, and then captured by the sensor again. And so you can generally attain much higher or better resolution of the observations because you're not relying on natural microwave emissions, which are a much lower energy source. Also, I should mention that the land sensing depth from microwave remote sensing is really dependent on the sensor frequency. Okay, so longer microwave wavelengths or lower frequencies tend to have a greater penetration depth into the land surface. Okay, and so that increases potential sensitivity to things like surface soil moisture, vegetation biomass, snow cover properties, and things like that. When we deal with higher frequencies, we're really more sensitive to surface skin temperature variations in, say, the vegetation canopy or the surface snow layer or the surface soil layer. So what's the source of the signal, this microwave freeze-thaw signal? Well, the primary source or the basis of that freeze-thaw signal is this large temporal shift that happens as in land surface dielectric properties or electromagnetic properties of the land surface between predominantly frozen and non-frozen states. That microwave signal is very sensitive to surface water, liquid water abundance. And so that dielectric of water, though, varies with microwave frequency, but it's nearly for liquid water, but it's nearly constant for ice. And so this graphic here in the upper left corner shows that this dielectric property here, the dielectric constant being in the left or the y-axis, and the microwave frequency going along the y or the x-axis here. What we see is that the dielectric constant of liquid water varies with frequency, but for ice it's relatively constant with microwave frequency. And so what we're doing is exploiting the difference between liquid water states or thawed landscape states where liquid water is present within the landscape medium in surface soil moisture or snow cover or vegetation biomass, and this frozen condition where the dielectric properties abruptly drop. And that is the big signal. That has a big impact from a passive microwave standpoint on the brightness temperature retrieval, and from an active microwave standpoint on the landscape radar backscatter return. And that freeze-thaw signal detects change, again, in that surface liquid water abundance. And that's really what we're detecting with this microwave freeze-thaw detection scheme that we have. And that freeze-thaw dielectric change or signal generally dominates the microwave seasonality of the landscape over other factors that would potentially influence liquid water abundance and dielectric properties. Things like vegetation biomass phenology, the seasonal onset of canopy leaf out, the growth of the vegetation canopy and senescence of vegetation canopy. That influences that dielectric property as well, but it's not nearly as large a signal as that freeze-thaw change. Other factors that might influence it: precipitation, snow or snowpack water equivalent, soil moisture variability. All of those factors can influence dielectric properties also, but generally for most land areas, that freeze-thaw signature, for most land areas where we actually have a seasonal freeze-thaw signature, that freeze-thaw change in dielectric properties is the dominant seasonal signature, and that's what we exploit with this microwave detection scheme. And what I've got here, this graphic on the right, just shows an example for JRS-1, which is no longer an active sensor. It was an L-band synthetic aperture radar And this is just an example over central Alaska. This is Bonanza Creek, Alaska. So it's a boreal landscape. And what we've got here is JERS was 100-meter resolution SAR. And so what we have here is just a subset of a 25 by 25 kilometer portion of central Alaska. And the top row here being the radar backscatter return, the bottom row here being the freeze-thaw classification, this temporal classification of changes in radar backscatter influenced by the change in freeze-thaw dynamics across the surface. And you can see that it's a sequence of early spring going from predominantly frozen conditions in February 17th, progressing to April 1st, a very rapid thaw during this period, which was also captured here with on-the-ground measurements of vegetation canopy temperatures. And what we have here in April 3rd, where the region is predominantly thawed. And what we're capturing here in this time sequence here is this series from February 17th, A, to April 1st, B, okay? And then, boom, April 3rd, we had a big regional thaw event, and that's captured by this very large change in radar backscatter on 3 to 5 dB, and that's a very large seasonal signal, and those are the types of observations that we're taking advantage of here. So what's the ecological significance of this freeze-thaw signal? What's the purpose? Well, our particular purpose, and what we've seen from this is an example from a stand-level study for boreal tower, the boreal forest being one of the largest biomes on Earth, existing predominantly at higher latitudes above 50 degrees north, where we have a very long frozen season. So that seasonal freeze-thaw cycle has a very strong impact on ecological processes. Okay, and this is for an example, tower eddy covariance CO2 flux measurement site in the northern old black spruce stand that was in Thompson, Manitoba. The tower is no longer active, or it's not active at present. And what we see here is the accumulation of net ecosystem exchange, or carbon flux, through time, extending from winter, January, all the way here into the summer period. And what it shows here is that we detect these primary thaw dates, and those are detected from surface measurements, but we also see the same signal from the overlying satellite microwave return as well. But as detected from the tower eddy covariance carbon flux measurements, what we have is that we tend to see large variability interannually in early springs and late springs, early spring thaws and late spring thaws. And the system up there is very keyed into that, and that it's an predominantly evergreen system. And so once that seasonal thaw onset occurs, and that seasonal thaw onset is indicated from ripening and rapid melt of the surface snowpack, that liquid water percolates into the surface soil layer and thaws out those surface soils, and the plants are ready to go. They have a very low albedo, and so the canopy is generally already thawed by the early spring when snowmelt starts to occur, and those plants are able to capitalize on that and come out of dormancy very rapidly. And that initiates a very strong uptake of carbon dioxide by the onset of seasonal photosynthesis in the spring. And the timing of that onset of photosynthesis has a very big impact on the annual carbon flux, the cumulative, whether the stand is a net source or sink for atmospheric carbon dioxide is largely dependent on the timing of that spring thaw event that occurs. Because that spring period, liquid water is abundant, solar radiation is generally abundant, and that's generally the period of the year when photosynthesis is maximized. And so what we see there is as that interannual variability progresses, we find that earlier thaw years generally promote carbon sink activity. And an early thaw year for this is an older stand, occurred in 1998, and we show there down in the lower left there that that stand was a net sink for atmospheric CO2. The negative flux denotes a carbon sink for the stand, and positive fluxes denote a carbon source to the atmosphere for the stand. And so the other years where later spring thaw occurred generally tend to be larger carbon sources on an annual basis, and that the latest year tends to be the largest carbon source of CO2 to the atmosphere. And so we see this very strong signal that spring thaw signal coincides with growing season initiation, and it influences ecosystem productivity and CO2 uptake at the stand scale. And we also see from the satellite microwave record that the seasonal frozen temperatures really constrain vegetation growth and land-atmosphere CO2 exchange for about 66 million square kilometers of the global land area. And that's over half the global land area that we're dealing with these freeze-thaw cycles with. So that was an example for the stand level significance for the freeze-thaw signal. But that signal actually propagates all the way up into the atmosphere. And this is another example, just looking at the overall Pan-Arctic scale. Again, we're dealing, this example is the all northern land areas above 45 degrees north, where the seasonal freeze-thaw signal for boreal, northern temperate, northern grassland, and Arctic areas is a big signal on a seasonal basis because of these kind of long, cold winters that these areas characteristically undergo. And this is looking at the NOAA CMDL carbon dioxide flask network at high latitudes. At higher latitudes, there's the seasonal variability that we see in atmospheric CO2 is actually very large, and it's dominated by vegetation net photosynthesis. And what happens is in the early spring, we see a very abrupt, large seasonal drawdown of atmospheric CO2 as the growing season begins and photosynthesis begins and pulls the CO2 out of the atmosphere. And what we're seeing here, this graph on the right here, is just looking at from the microwave standpoint, the timing of that primary thaw event in spring and its relationship to the timing of atmospheric CO2 drawdown in the spring from the NOAA CMDL observatory overall, over the whole domain. And what we see here is that generally earlier thaw years denote earlier and larger drawdown of atmospheric CO2, so greater carbon sink activity. Later thaw years generally are associated with a smaller and later CO2 drawdown of atmospheric CO2. So we see this freeze-thaw signal propagating into the larger regional and global CO2 cycle. So our motivation for building a long-term global freeze-thaw cycle is that first, satellite microwave missions have been operational since the mid-1970s, approximately 1979, for regular global observations. That's one of the longest records available to us from satellite remote sensing, both optical and microwave. And so that enables a potential construction of a long-term freeze-thaw record spanning more than 30 years. Okay? And so the benefit of a longer observational record that's regular and consistent and well-calibrated allows us to separate out longer-term climate trends from shorter-term, large interannual climate variability and periodic climate oscillation-driven changes in environmental cycles, things like ENSO and other types of natural climate variability. So it behooves us to have a longer record for these types of things. And then we also find that there's a number of previous studies that demonstrate this strong link between the satellite microwave freeze-thaw signal and potential growing season changes. Global warming coincides, generally what we found is that it coincides with earlier and longer growing seasons or potential growing seasons, and that's been linked with positive northern greening trends, for example. But there's also been some evidence of increasing drought stress. And we also see that there are these freeze-thaw linkages with a number of other ecosystem processes, including water cycle changes, things like evapotranspiration, changes in seasonal ice break of large rivers and lakes, the timing of then significant flooding in the spring, changes in seasonal snow cover dynamics, as well as propagating into both plant phenology changes and animal migrations as well. So there's a large potential realm of exploration that could take advantage of these types of data. But what we need is an accurate freeze-thaw record with sufficient length and resolution to diagnose climate change-related trends and impacts. And so that's the primary objective. And what I've got over here on the right, this is the estimated freeze-thaw affected regions from global reanalysis temperature data. Okay, and what it shows is basically that about 52% of the global land surface is affected by seasonal freeze-thaw cycles of at least 5 or more days of frozen conditions per year, which has a significant impact on ecosystem processes. Okay, and this forms the primary basis for our freeze-thaw global domain for the data record construction. Okay. So our overall goals and objectives for this particular database construction was to utilize the available global satellite microwave remote sensing data records to develop a consistent long-term global record of landscape freeze-thawed state dynamics. And because our primary focus was for ecosystem properties, we primarily, for this case, looked at vegetated regions where frozen temperatures are a major constraint, or identified as a major constraint to ecological processes. And we wanted the ability to distinguish freeze-thaw climatology and heterogeneity in accordance with mesoscale climate terrain and land cover features. So that was in accordance with the limitations and somewhat of the passive microwave remote sensing, that we're really dealing with coarser resolution fields of view with these types of sensors because of the low level of microwave emissions from the land surface, as I mentioned previously. And we wanted to quantify freeze-thaw linkages, the ability to quantify freeze-thaw linkages to ecosystem processes, things like vegetation, productivity, respiration, and carbon exchange. We wanted also the record to be of sufficient length to distinguish this natural climate variability, which tends to be very large at higher latitudes, from longer-term climate change signals, which tend to be a much more subtle signal. So we wanted to be able to separate those two signals from each other, and the only way to really do that is to get beyond about a 30-year record. So just a method summary. To assemble this record, we really exploit similar passive microwave brightness temperature retrieves from overlapping satellite sensors. And what we've got here on the lower right is this is potentially all the satellite microwave sensors that are available to us potentially to assemble these types of records. And this includes both active and passive sensors. Both sensors that have been operational in the past that may no longer be operating, as well as sensors such as the NASA Soil Moisture Active Passive mission, which have a planned launch in November of 2014, but is not yet available to us. What we exploited for this particular record was consistent brightness temperature measurements at the same frequency, and we got that information primarily from the Special Sensor Microwave Imager, which is a series of NOAA DMSP platforms that's currently still operating, but began operating in 1987, with an earlier set of similar observations from the Scanning Multi-Channel Microwave Radiometer, or SIMR. Okay? And those two sensors were overlapping for almost a year, and so we exploit that overlapping record for empirical calibration of similar observations from both sensors, because we wanted to be able to develop a very well calibrated freeze-thaw record and not have systematic bias depending on which particular observation platform we happen to be switching over to over the course of this multi-platform and multi-year time series. Okay, and so we incorporated a pixel-wise temporal brightness temperature change freeze-thaw classification, and that's a temporal change classification from reference frozen and non-frozen conditions. And we used a consistent microwave frequency. We adopted the 37 gigahertz or K-band frequency observations that were common between SIMR and SSMI to develop this record. We could have done it other ways using different frequencies, but the 37 gigahertz frequency is a higher frequency. It's very well correlated to surface temperature conditions, as well as the freeze-thaw being very sensitive to liquid water abundance in the land surface. But it doesn't have the relative depth of penetration, say, into surface vegetation and soil conditions that lower frequencies like L-band would have. And we primarily exploited, again, the SIMR and the SSMI instruments. SIMR going from, or extending from 1979 to 87, and then the SSMI series of sensors initiating in 1987 and extending into current operations. And so we're continuing to do updates to the data record as new SSMI data come available. And then we adopted an empirical brightness temperature calibration of those overlapping records. and then we applied this freeze-thaw classification scheme. And we adopted, each sensor has an ascending and a descending orbit. We treated those orbits separately for the calibration and the freeze-thaw classification. And then we applied a daily composite of those resulting AM and PM orbit freeze-thaw classification data into this composite daily record, and I'll talk about that in a minute. And then we used, we wanted to do a regular global daily validation of a freeze-thaw classification accuracy that's incorporated into the product. And to do that, we use surface air temperature observations from daily weather stations extending over the globe, more than 3,700 weather stations potentially available to us at any given time on a daily basis. Those are the types of observations we used. And we used daily minimum and maximum air temperatures to correspond with the AM and the PM overpass, orbital overpass satellite observations and retrievals of freeze-thaw dynamics. And we also, for calibrating the freeze-thaw record, we actually use surface air temperatures from global reanalysis data to calibrate those reference frozen and non-frozen states on a grid cell-wise basis that were then used to apply the freeze-thaw classification algorithm on a daily basis. And the set of equations that I've got here just is an example of what the freeze-thaw classification algorithm looks like. It's actually a very simple temporal change detection algorithm, and again, it's a temporal change of brightness temperature in this case from reference frozen and non-frozen conditions. So you're looking at the potential difference in brightness temperature between these reference conditions for any given day, what the brightness temperature retrieval is relative to those reference conditions, and whether that difference from those reference conditions exceeds this freeze-thaw threshold, determining whether it's frozen or non-frozen, that land surface. And again, this algorithm does not distinguish subgrid scale heterogeneity within the satellite field of view. So we're not actually distinguishing a soil freeze-thaw condition from a snow freeze-thaw condition or a vegetation freeze-thaw condition. We're just looking at the bulk liquid water abundance within the satellite field of view, whether it's in soil, snow, or vegetation, other than that we're using a 37 gigahertz frequency retrieval, which tends to be more surface conditions rather than deeper soil layer conditions. So this is just a summary of the global freeze-thaw data record for a selected number of days here on the right. And we've got just an example of the global record. And again, the domain that we're seeing, the colored areas, was identified earlier from as areas of the land surface, vegetated land areas, where seasonal frozen temperatures are a significant constraint to ecological processes. And so for portions of South America and Africa where we very rarely ever have any freeze-thaw conditions, those areas are really not part of the classification domain. And so we've got three sequences, just an example days here, of April 10, June 19th, and December 26 of an example year, 2004, just showing the spatial patterns of frozen conditions, non-frozen conditions, classified transitional conditions, and that's a condition where we have frozen conditions in the AM overpass, the morning overpass, and had thawed out by the afternoon overpass, and we call that a transitional condition. And we also have inverse transitional conditions that are identified from those AM and PM orbital freeze-thaw classifications, and that's exactly the opposite, where we had non-frozen or thawed conditions in the morning and then frozen conditions in the afternoon. So what that entails is for this product we have 4 discrimination levels. That frozen condition where it was frozen both in the morning and the afternoon overpass, thawed conditions where it was thawed both in the morning and the afternoon, transitional conditions, and inverse transitional conditions. It also has a global domain. It encompasses, again, all those freeze-thaw affected areas, or about 52% of the global land area, vegetated land area. It also, the resulting data record is nearly continuous. It's calibrated. It's a daily freeze-thaw record. It spans more than 30 years, from 1979 to 2012 currently, and again, with continuing updates as the SSMI record continues to lengthen. And the data is provided in a consistent global projection. It's a global EaseGrid version 1 projection at this point, and a 25-kilometer spatial resolution. The natural resolution, or the field of view observation at the 37 gigahertz, is really about 12-kilometer resolution. So there's potential for enhanced resolution products in the future. And the freeze-thaw database and accompanying metadata is all available online for public access, and it's available in two areas. It's posted to the NSIDC, or the National Snow and Ice Data Center, and it's also posted to online data archives at the freeze-thaw project page at the Numerical Pterodynamic Simulation Group at the University of Montana. And that particular website has additional ancillary information for user interrogation of the data products, visualizations, PowerPoint presentations, and things like that. So, but the actual data record is the same between both locations. So just an example of how freeze-thaw classification accuracy of this record is assessed on a daily basis. And again, it's determined from the global weather station network. Every day, weather stations are interrogated online, the data are downloaded, and we do a pixel point comparison between the overlying grid cell freeze-thaw retrieval and the surface weather station-based daily minimum and maximum air temperature, as determining whether that air temperature is above or below a 0-degree freeze-thaw threshold. And what I've got here is a general summary of what those metrics look like on a global basis. This information is incorporated into the product information on a daily basis. And what we see here is just a summary of, this is just looking at all the sites spanning the weather stations over the globe that we're using for the particular validation. And the metrics here are aggregated to a mean annual classification accuracy. And so what you're seeing there is generally higher accuracy at lower elevations and lower latitudes, but that's really an artifact of that those areas tend to be non-frozen for a greater portion of the year, and so the overall mean annual classification accuracy tends to be higher there, because we do very well when things are predominantly frozen or non-frozen. But really what we find is that, and what we have here on the upper right is a look at the global freeze-thaw classification accuracy over the course of the year. And what you see is the classification accuracy, the spatial classification accuracy relative to all these weather station sites tends to decrease as during these seasonal freeze-thaw transition periods in the spring and in the fall. And that's generally when spatial heterogeneity in freeze-thaw processes is maximized. And what we see also is that shows the freeze-thaw classification on a daily basis for both the AM and the PM orbital retrievals. And it looks like from this figure that the AM retrieval has a lower classification accuracy, but that's again really an artifact of the fact that for minimum air temperatures, they tend to spend a lower portion of the year as predominantly non-frozen. So it's really just an artifact. When we actually look at these side by side, the spatial classification accuracies are actually the same between both the AM orbit and the PM orbit for the most part. And what we have here is just looking at the accuracies through time, from 1979, the initiation of the record, through the, in this case, it's just through the mid-2000s. And the gray shading there denotes the spatial standard deviation over the globe, over the global freeze-thaw classification domain and the accuracies. But overall, what we see is a spatial classification accuracy that's greater than 80%. And what we also see is a slightly positive trend in accuracy through time, and that's really, again, an artifact of the fact that over the past 30 years, global temperatures have increased, and so this non-frozen or frost-free period is generally increasing on a global basis. That's producing an artifact of higher mean annual classification accuracies, even though the daily classification accuracy isn't really changing much. And then the product provides these kind of point scale global assessments of freeze-thaw accuracy, but the product also provides a spatially contiguous map of overall product quality, and that's really was derived from an empirical approach where we estimated product accuracy from a variety of ancillary information, including terrain heterogeneity and land cover heterogeneity, the proportion of open water within each grid cell. All of these factors were determined to potentially degrade the freeze-thaw accuracy, and we used that information to predict overall product quality. And those metrics are derived on an annual basis, and they're included with the product as well. So one potential effect or influence on freeze-thaw classification accuracy is the relatively coarse footprint of this 37 gigahertz passive microwave retrieval of freeze-thaw dynamics. where that classification is currently being derived at a 25-kilometer resolution. So we wanted to do an investigation of what the reduction in potential accuracy is because of that coarse spatial scale relative to potentially higher resolution retrievals that we might get from radar. And here's an example that we looked at for Alaska. This is using the ALOS pulsar sensor, which was a 100-meter resolution SAR over Alaska, and this is a freeze-thaw classification, an example for April of 2007. The drawback of satellite or current SAR sensors is that while we have higher spatial resolution, we generally have lower temporal fidelity for global observations. And so this was derived from monthly composited data over Alaska. And it's a freeze-thaw classification map, the blue areas being predominantly frozen and the red areas being predominantly non-frozen conditions. And the yellow boxes there on the right are selected boxes that were predominantly frozen, intermediate, and predominantly non-frozen conditions. And we did an investigation of what the relative footprint size of the freeze-thaw classification, what effect that has on apparent freeze-thaw classification accuracy, spatial accuracy. And that's showing here. And it's a log plot, so there's a log of the pixel size here on the x-axis, and there's the relative classification error on the y-axis. And what we find is that there's a relatively rapid drop-off or decrease in classification accuracy, or classification error, I'm sorry, as we move from approximately 1 kilometer resolution down onto the order of 100-meter resolution, which was our baseline fine-scale resolution. And that's an indication that as the retrieval approaches the natural scale of landscape heterogeneity in the freeze-thaw processes, and that's on the order of a hill slope scale, we start to see greater accuracy or less classification error. And as we reach really beyond 1 to 3 kilometer resolution, the overall classification error is relatively flat. So what that means is that there's probably not much difference in classification accuracy between a 25-kilometer retrieval and a 10-kilometer retrieval, but there's probably a big classification difference between a 10-kilometer retrieval and a 3-kilometer resolution retrieval. Okay, and we also see what each of these lines refers to. Again, is each one of these boxes. Okay, and we see then that we have a larger classification error in this area that's more heterogeneous in terms of mixed frozen and non-frozen conditions. And what that indicates then is first that the classification error tends to be larger during these spring-fall transitions, and it's also larger over complex landscapes, complex terrain, and complex land cover vegetation characteristics. But that overall, this spatial scaling error is less than 20% at this 25-kilometer resolution that we've looked at. So that's consistent with this overall 80% freeze-thaw classification error that we're seeing over the global domain. So just an example application is really, now that we have this long-term record, we can look for the first time at what the freeze-thaw seasonal climatology is from this record. And that's just what we see here on the left side, upper left here of the slide. This is the mean frost-free season as determined from the long-term record. And in the lower left here, we have the non-frozen season, standard deviation of the non-frozen season variability year to year. And what you see then is certain areas have very large interannual variability, even if they have a very long or relatively long frost-free season. And so we know from ecosystem studies, which I'll kind of highlight here, that variability tends to have a big impact on ecosystem processes. And from the record, because we have a relatively good, well-calibrated record in terms of cross-sensor calibration, cross-platform calibration, and then demonstrated accuracy, that we can start to assess long-term environmental trends over this 30-plus year record. And that's what I'm showing here, is just for that northern hemisphere domain on the left, this is what we're seeing on the aggregated non-frozen or frost-free season trend over that 30-plus year record. And overall, what we're seeing is about a 2-day per decade increase in the frost-free season over the domain. The gray areas there represent, we also, to do some assessment, we compared what that increase in the non-frozen or frost-free season is relative to global temperature observations or simulations from the global reanalysis data sets. And we used a number of global reanalysis data sets to look at to compute a mean, and the gray area, the gray shading in that plot, denotes the range of variability from the reanalysis data sets. But overall, that increase in the non-frozen season or frost-free season corresponds with about a half degree of warming per decade over the domain as well. So we're seeing very similar things, but from completely different sources of information. And that increase in the non-frozen season, what we found, is primarily due to earlier springs arriving overall over the domain rather than later falls. So just an example, ecological application. We've seen this link between, or this inferred link between freeze-thaw dynamics and vegetation productivity. And this is just an example for a northern domain. So looking at all land areas above 45 degrees north, so northern temperate, boreal, and Arctic land areas. And what we see here is the correlation on the left map here is the correlation between the frost-free season or non-frozen season is determined from the freeze-thaw record versus summer growth anomalies from the satellite NDVI record. And this was an example. This is an NDVI record that's been developed at the University of Arizona, and it's part of the NASA Making Earth System Data Records for Use in Research Environments program, which is the same program that the freeze-thaw record was developed under. So it's a good example of comparing these new environmental data records together and for synergistic studies. And what we find is that we tend to find this very strong positive correlation between changes in the non-frozen season or frost-free season and summer growth in the NDVI, and the NDVI being a surrogate for vegetation productivity in this instance. And where we see this direct relationship, that's indicating where earlier and longer non-frozen seasons or frost-free seasons tend to promote greater NDVI growth or vegetation growth. And that there's other areas, though, those areas in kind of the yellow and red there, where we actually see the opposite response. And those tend to be drier grasslands and drier boreal, southern boreal zone areas, where earlier and longer non-frozen seasons may actually promote water stress because of this longer period of evaporation and potentially warmer temperatures. And that's really explained when we start to look at this is just taking the global reanalysis data available to us, temperature data, and atmosphere vapor pressure deficit data, which is used by us as a surrogate for atmosphere moisture demands, or as a moisture index. And we estimated the dominant climate constraints to vegetation productivity, NPP, from both in terms of a water stress factor and a cold temperature stress factor. And what we find is these kind of overall long-term climatological trends and patterns in those data tend to explain very well the spatial heterogeneity we see in this correlation between summer growth changes from NDVI and frost-free season variability from the freeze-thaw record. This is just an example of another application of the freeze-thaw record. Because we're obtaining freeze-thaw information globally on a regular basis, on a daily basis, actually on a diurnal basis, we're able to exploit those types of observations to get these to do some types of assessments of transient type extreme events. And here's an example of that. This was a well-documented late spring frost event that occurred in 2007 across significant portions of the southeast USA, across 9 states in this instance. And what we have up here in the upper left is the MODIS NDVI sequence over this transient frost event that occurred. And what this was in early April, we had a very early spring in that particular year for this region. And so there was an early green up indicated from the MODIS NDVI record and was corroborated on the ground. Farmers were planting their fields and things like that. And what happened was this transient frost event came down, and over a period of a few days caused large widespread crop mortality and widespread canopy defoliation of these hardwood forests throughout the region. And that is propagated up into this NDVI signal from MODIS, which shows this relatively abrupt drop in canopy greenness and retreat in phenology post-freeze relative to the the early spring conditions. And so in looking at the freeze-thaw record, what we see here is kind of the case study. Over the same period, we see that frost was really this transitional frost condition where it was thawed out during the day, but it refroze at night. And it occurred widespread primarily over the early April period from April 6th to April 9th. And it was primarily driven by this big air mass that came down from the northwest, moving across the Great Lakes states there to the southeast and east. And what we see, because we have a long-term freeze-thaw record, we're actually able to assess that transient event in terms of how extreme was that event relative to the long-term 30-plus year record. And so what I'm showing here in the upper right is just a graphic of the proportion of those 9 states that was identified as frozen, okay, the proportion of area that was frozen in the y-axis here relative to time in the x-axis. And the areas that we're computing the proportion is over these 9 southern states. And what we see here is the area in blue was that extreme frost event that occurred in the early spring in 2007, and that affected up to about 35 or more than 35% of those 9 southern states. And that was well beyond the 31-year mean climatological conditions for those 9 states, which is identified here in the red. So with this particular record, we're actually able to do these kinds of transient studies as well as these long-term kind of climate trend assessment studies. So in summary, this freeze-thaw record provides a consistent daily record of landscape freeze-thaw dynamics, and it currently encompasses global vegetated land areas where seasonal frozen temperatures have been identified to influence ecosystem processes significantly. The product includes detailed quality metrics on classification accuracy and estimated data quality over the global domain. And it's a sufficient record length at this point, it's more than 30 years, to be able to distinguish climate trends, spatial and temporal anomalies, seasonal, yearly, daily anomalies, and associated ecosystem impacts. There are diverse application areas indicated from the current literature that have studies that have already used this particular data product. Those studies have included vegetation phenology and productivity related studies, looking at variability in carbon, methane, and CO2 fluxes over the land areas, evapotranspiration, snow and ice and hydrologic impacts, and animal interactions affecting caribou migrations and muskox foraging habitats and things like that. So there's really a diverse set of applications potentially available to use this record. And currently there's probably unexplored applications as well. The limitations we currently have that we've identified are really that we're dealing with this relatively coarse field of view and passive microwave retrieval that's on the order of 25 kilometers resolution. It's also dealing with a higher frequency observation, 37 gigahertz or the K-band frequency retrievals. And so we're not as sensitive to those deeper soil layer conditions as we might like if we wanted to look at soil freeze-thaw dynamics and be able to isolate that. And again, it's a bulk freeze-thaw retrieval of the landscape. So we're not distinguishing snow, soil, and vegetation conditions for this particular retrieval. It's just a bulk retrieval and observation. The planned updates that we have for this product that we're currently planning to do are to continue the data record with, again, ongoing special sensor microwave imager observations as that operational record continues. We're also incorporating a larger global domain, so we're extending the domain into snow and ice areas, particularly at higher latitudes, Greenland and places like that, to start to look at how ice and snow freeze-thaw dynamics may be affecting regional hydrology and climate dynamics. But that product won't be available for a bit yet. But check the website, the project website, and the NSIDC pages periodically for updates. And we're also promoting or planning an enhanced resolution product for northern land areas for regional studies. And that'll be initially probably on the order of a 12-kilometer resolution product consistent with the inherent field of view of the 37 gigahertz retrieval that we're looking at, but potentially higher resolutions as well as we look at regional downscaling applications. And then I'll just leave you with some selected online resources for further exploration. One is, again, the Freeze-Thaw Earth System Data Record at NSIDC, and the National Snow and Ice Data Center also maintains a set of interactive web tools that you can get in and interrogate the data sets in relation to each other. And then the Freeze-Thaw project page at the University of Montana also has a variety of tools, web tools, and support presentations and data sets that are potentially useful for further exploration. Thank you.